Okay, so now that we've looked at the different ways we can represent our organic compounds, we're going to look a little bit more in detail at the differences between types of organic compounds. So we're going to focus on hydrocarbons, which are compounds that contain only carbon and hydrogen atoms. So remember from earlier in the session, these can be represented as straight chain structures or as ring structures. And as I'll show you, this actually dictates how many hydrogens are actually going to be able to attach to the carbon atoms. So hydrocarbons, what are they? Well, they're organic compounds that contain carbon and hydrogen atoms. And there's two types. We can either have saturated or unsaturated hydrocarbons. And these are what we need to make a distinction between. So the definition of a saturated hydrocarbon is one that only contains single carbon-to-carbon bonds. And for that reason, they're relatively unreactive. So they're not going to react readily with other compounds. And this is because a large amount of energy is actually going to be needed to break those single carbon-carbon bonds before other atoms can be added in their place. Unsaturated hydrocarbons, however, don't just have single carbon-to-carbon bonds. They're going to have one or more of these double or triple carbon-to-carbon bonds. They'll also contain single carbon-to-carbon bonds, but the key is for an unsaturated hydrocarbon, it doesn't just contain single carbon-to-carbon bonds. So there's going to be a double or a triple carbon-carbon bond somewhere in that structure. And because of the presence of this multiple carbon-to-carbon bond, it actually makes these structures more reactive, more likely to react with another compound. And this is because these double and triple carbon-carbon bonds can actually be broken more easily than a single carbon-to-carbon bond in a chemical reaction. And by doing this, we can actually add in other atoms by forming new covalent bonds, which is something we'll explore a little bit more in a later session. But essentially, to summarize, saturated hydrocarbons, only single carbon-to-carbon bonds. Unsaturated, more reactive because they have this double or triple carbon-to-carbon bond. So saturated hydrocarbons with only single carbon-to-carbon bonds, they're the ones that are unreactive and stable. And we can see a representation of one of those here, where we've got 3 carbons and there's only single bonds between each carbon in that structure there. So if we compare this to the unsaturated hydrocarbons that are more reactive due to the presence of a multiple carbon-carbon bond, we can see that down the bottom here, we've got 2 of the carbons that are connected by a double carbon-to-carbon bond. And that's what makes this structure more reactive, because one of these bonds within that double carbon-carbon bond can actually be broken and therefore allow other atoms to be added in its place. Notice also that this unsaturated hydrocarbon does have a single carbon-carbon bond. So if it's unsaturated, it doesn't mean they're all double or triple bonds, but some of them will be, at least one. So interestingly, with our saturated hydrocarbons, that means they have the maximum number of hydrogen atoms bonded to the compound possible. And this is because they have limited bonds to other carbon atoms. So we can say that these structures are saturated with hydrogen atoms. That's because they have the maximum number of hydrogen atoms attached. So because the carbon atoms only connect to one other carbon atom, all the other bonding positions can actually be filled by hydrogen atoms. So notice here that the carbon is bonding to 3 and then 2 and then 3. So once the carbons have connected to each other, this is the maximum amount of hydrogens that can actually be bonded to. And that's why we say it's saturated with hydrogen. So we call this sort of structure an alkane if it's in this straight chain form. But if it's in a cyclic form, like this ring structure here, which also has the maximum number of hydrogens attached, we call it a cycloalkane. Cyclo meaning ring. So the example of the compound here that's an alkane that we're looking at is actually propane. So here we can see a few of the different representations that I showed you earlier in the lecture. So we've got the molecular formula, which is C3H8, and if we put it into the condensed structural formula, then that goes to CH3, CH2, and CH3. So remember, the N's here are the ones that are the CH3s, and then in the middle we've got a CH2. So what's significant about this is that the ends of the compound have CH3, whereas the middle only has CH2. So why is it the ends have CH3s, whereas the middle has CH2? It's because the ends only have one bond to another carbon, whereas the middle has bonds to two carbons. So keep this in mind, because we're going to have a look at a structure that doesn't actually have any CH3s. And let's work out why this is. So another version of a saturated hydrocarbon here is a cycloalkane. So the structure we're looking at here is cyclohexene. So in the condensed structural formula here, we can see that all the carbons are actually CH2s. That means there's actually no N's present at all. So why are there no N's present in this compound? It's because each carbon is actually attached to two other carbon atoms. That's what allows it to be a ring structure. So by definition, there are no N's, so no CH3s. So what this means is, in comparison to a 6-carbon compound that was drawn in a straight line, like this, so this is a straight chain structure that contains 6 carbon atoms. If we drew in all of the carbon atoms and the hydrogens, there'd actually be less hydrogens in the ring structure than there are in this straight chain structure. And why is that? Well, it's because the straight chain structure has these CH3 ends, whereas the cyclohexane structure has no ends. So essentially what this means is the ring structures have less hydrogens than the corresponding straight chain structure, because more of the bonds are being taken up by bonding between carbon atoms. So remember, when we're looking at all these structures, that each carbon has to have 4 covalent bonds and hydrogen has to have 1, going back to what we were looking at the start of the session. So now let's have a look at a little bit more detail at the unsaturated hydrocarbon. So remember, these are the structures that have one or more double or triple carbon-to-carbon bonds, as well as single carbon-to-carbon bonds. So we say that these structures are actually unsaturated with hydrogen, so they don't have the maximum number of hydrogen atoms attached. And this comes back to the fact that they have these multiple carbon-carbon bonds. So if you have more bonds to carbon, by definition, there's going to be less space for hydrogen to bond. So if we look at these two carbons here, there's a double bond between these two carbons. Essentially that means there's only 2 other positions where they can form covalent bonds. So we've got attachment to 2 hydrogens from this one here, and attachment to a hydrogen and a carbon from the other one. How is this different to what we saw in the alkane? Well, remember, there was a hydrogen attached down the bottom here and also another one here. But now there's actually no space for those hydrogens because we've got the extra bond between the 2 carbons. So essentially this means that there's going to be 2 less hydrogens in a alkene, which is a hydrocarbon with a double bond, than there would be for the alkane that had the same number of carbons. So wherever we have multiple carbon-carbon bonds, essentially that means there has to be less hydrogens attached. So we're taking away bonding positions for hydrogens by having double or triple carbon-carbon bonds. You can see the same thing in ring structures like this cycloalkene here, where the double bond between the 2 carbons here up the top is actually meaning that each of those carbons only has space to bond to one hydrogen atom, because the other bonds is two carbon atoms within the ring. So essentially, instead of being CH2s, those two carbons at the top here are just CH, one less hydrogen than we saw in the structure here, where so each of these ones at the top here was CH2s, whereas if you look at the cycloalkene structure here, we've actually got CHs, not CH2s, due to the presence of that extra carbon-to-carbon bond. So we're now looking at a alkene here, and it's propene because it has 3 carbons. We'll look into a little bit more of the naming nomenclature for the number of carbons in a compound in a later session. But essentially, because of the presence of that double bond, we now have less hydrogens attached. So instead of being C3H8 like the previous structure was, it's now C3H6. So we've got 2 less hydrogens. The condensed structural formula looks different too as well, because we've got a CH2 and then a CH rather than CH3, CH2. And essentially this is because it has 2 less hydrogens than the corresponding saturated hydrocarbon. So I'll just draw out that saturated hydrocarbon for a comparison. So remember, for the alkane version where it was saturated, all of the bonding positions besides one carbon-carbon bond to each carbon was filled by hydrogen. So you can see here that there's all single bonds and therefore more bonds to hydrogen than we have in here for propene. So here we have our cyclohexene, which is a ring structure version of an alkene structure that is an unsaturated hydrocarbon. So again, it has 2 less hydrogens than the saturated version. So if it was saturated, it would be C6H12, but because it's unsaturated, it's actually C6H10. So you can see at the top here, where we've got the double bond, it actually means we have CHs present rather than CH2s. Again, meaning there's 2 less hydrogens in the compound than there would be without that double bond. Alright, so now another exercise to have a go at to see whether we've got this idea of the difference between these different saturated and unsaturated hydrocarbons that we've introduced. So the task here is to identify which of these 4 is an alkane, which is a cycloalkane, which is an alkene, and which is a cycloalkane. So I'll give you a little bit of time now. Please pause your recording and try and work out which is which. So let's start with number 1. So number 1, we have carbons connected by all single bonds, and we've also got a straight chain structure. So these are features that we see in an alkane. So an alkane is one of the types of the saturated hydrocarbons. So it's saturated because it only has single carbon-carbon bonds, meaning all other bonding positions are filled with hydrogen atoms. What about number 2 here? So we've got a ring structure. I've actually shown the carbon atoms in this case, so it's in a condensed structural formula, and we've got a combination of double carbon-carbon bonds and single carbon-carbon bonds. So we know it's going to be a cyclo because it's a ring structure, but is it going to be a cycloalkane or a cycloalkene? So because of the presence of these double carbon-carbon bonds, that tells us that it's going to be an alkene rather than an alkane. So what we have here is a cycloalkene, which is one of the types of unsaturated hydrocarbon. What about number 3 here? So here we've got a structural formula that is condensed. So one of the ways to work out whether this has double bonds or not is to actually draw out the whole structure. So some people might be able to work this out without drawing it out because of the presence of this CH and CH2 at the end here. Basically tells us that there's going to be a multiple bond at the end here. But let's draw it out anyway. So the first one from the left hand side is a CH3, and then the next one is a CH2. So all single carbon-carbon bonds so far. And then we have a CH. And the last one is going to be a CH2. Okay, so let's focus on these last two carbons here and check whether they have enough bonds. So this carbon only has 3, 1, 2, 3, and this carbon also only has 3. So it's logical that there's going to be another bond there. So we've got now a double carbon-carbon bond between these two carbons. So what we actually have in this structure is an alkene. And it's in a straight chain form as well. So we would call this an unsaturated structure, specifically an alkene. And number 4 here we have a line bonding formula. So it's in a pentagon shape. So what this actually represents is 5 carbons connected in a ring structure like this. There would be associated hydrogens as well. But because there's no double line, that tells us that it's going to be a saturated structure rather than unsaturated. So what we actually have here is a cycloalkane. So you can see how from these 4 groups we've got very distinctive different structures. So hopefully that gave you a bit of a way of working out what some of the differences were, and looking for either the presence of these double bonds or the absence of hydrogens to know that it's not saturated, it's actually unsaturated, doesn't have the maximum number of hydrogens present. So we've reached another Participation Plus question. So remember, these are a really good way of revising the concepts, trying to put it all together and making sure you understand it. So make sure you share your answers with other people in your online cohort and get some feedback on your answers too. These types of questions can help you a lot and make sure that you've understood what we've been through. We also have some more tutorial questions to have a go at. So via the LMS, if you go to your revision quiz for session 7, attempt now questions 5 to 8, and that'll give you a good understanding of how you've been going as we've been progressing through this session. So to summarize this part of the session, looking at the different ways we could represent compounds. Remember, we saw the molecular formula, which simply had the number of each type of atom present. We also saw the complete structural formula, which is where we had all the lines present showing each covalent bond in the compound. The condensed version was similar to the complete version, but then we were showing things as CH2 and CH3 rather than showing all the bonds. And then we saw the line bonding formula, where the bonds between carbons are just represented as a line. So you can imagine that there's a carbon at the end point of each line in those structures. Most recently, we've been looking at the differences between saturated and unsaturated hydrocarbons. So if it's saturated, it's only got single carbon-to-carbon bonds, meaning the maximum number of hydrogen atoms can attach to the carbons in the structure. And we saw that there were alkanes and cycloalkanes in this group. Whereas the unsaturated hydrocarbons, those are the ones that contained multiple carbon-carbon bonds, so either a double or triple carbon-carbon bond. Remember also that they will contain some single carbon-to-carbon bonds. Because of the presence of these double bonds, the unsaturated hydrocarbons are going to have less than the maximum number of hydrogens. Because remember, if you have more bonding between carbons, there's less room to bond with other atoms. And the groups that we saw had these characteristics were the alkenes and the cycloalkenes.